Hey everyone, welcome back to Everything's Relative with me, Mr. K. Today we're going to be looking at some topical past paper questions on the topic of magnetic fields, and these past paper questions come from the Papa Cambridge website. Now I'll leave a link to these question papers in the details below, so you can download this paper, and my suggestion would be to work with these questions before you watch me go over the solutions. So use these questions as revision, as preparation for your final exams, which for many of you will be in a few months' time. And then you can watch this video if you get stuck, or if you need a clearer explanation than you'll get from your regular mark schemes as to how to go about answering these questions. You know that many of these questions are also repeated, so I'm just going to ignore the repeated questions, but I will specifically let you know which questions I'm working with as I'm working with them in order. I'm not going to be able to do all in this video, but I'll do a few, move on to another topic, and when I'm done with all the topics, we'll come back to each of the topics that are incomplete. So this is the topic of magnetic fields, which is the longest topic in A-level physics. And as you know from A-level physics, we can't go anywhere without our left-hand rule, so I've just added out a little diagram of the left-hand rule here so that I can use it to refer when required. And Fleming's left-hand rule, I'm just going to write down each of the directions. The thumb gives me the direction of the current. My forefinger gives me the direction of the magnetic field, B, and my middle finger gives me the direction of current, I. So I'm going to keep this for whenever I need it. So the first question I have is from, it's not very clear here, but I'm just going to write it down. This is, as it's numbered in these Papa Cambridge questions, it's question 251. And this is from paper 9702, which is the subject code for A-level physics, Cambridge A-level physics, winter of 21, which is November 2021, question paper 4.1, question paper 4 being the long structured questions for A-level physics, and this is question number 8 in that paper. So if you can't, for some reason, use the Papa Cambridge questions, you can look for the specific question. And the first question, as always, is sort of a build-up, define, state, etc. And they asked me to define the Tesla. So actually, before I define the Tesla, a way to remember how I can define the Tesla is to remember that when I place a current-carrying wire perpendicular to a field, a magnetic field, it feels a force BIL. In general terms, if it's not perpendicular, it's BIL sine theta. F is equal to BIL sine theta. And I can find the definition of flux density by rearranging this equation and writing it as B is equal to F over IL sine theta. And what I can see from here, therefore, is that the units of B, I'm going to use square brackets to denote units, is a Newton over an ampere meter, a Newton per ampere per meter. So that can help me actually in the definition. Again, these definitions are things that you can just sort of memorize, but you could also use your knowledge of the topic to write this definition. So a Tesla is a unit of measurement. I mean, we can say the unit of measurement of magnetic flux density. It is the unit of measurement of magnetic flux density. That's the first point that I would write. And what it is exactly is, now be very careful, the questions ask me to define the Tesla, not to define the magnetic flux density. When defining a unit of measurement, define it in terms of other units. So it is a Newton per ampere per meter for a current carrying wire. Now I'm going to assume that the sine theta is equal to 1, so theta is 90 degrees, so that the wire is placed perpendicular to the uniform magnetic field. So if sine theta is simply 1, then I can assume that the wire is placed perpendicular to the uniform magnetic field. Uniform because B is constant. So if I place a So 1 Tesla is the Newton per ampere per meter for a current carrying wire that's placed perpendicular to a uniform magnetic field. Now, be careful of saying things like a force per ampere per meter or a Newton per ampere per length. Don't mix up quantities and units in your definition. Since we're defining a unit of measurement, define it in terms of other units of measurement. Tesla is a unit, newtons are units, amperes are units, and meters are units. So be very wary about how you define units and how you define quantities. So now we are told that a stiff metal wire is used to form a rectangular frame. So we have basically a frame of wire measuring 8 by 6 centimeters. The frame is open at the top and suspended from a sensitive Newton meter as shown in the figure. The open ends of the frame are then connected to a power supply. So the top ends are connected to a power supply. And there's a current of 5 amperes in the frame as in the direction as indicated. So down at the left towards P and then up at the right. That's the direction of the current. The frame is slowly loaded into a uniform magnetic field of flux density B so that all of side PQ is in the field. The magnetic field lines are horizontal, underline this word, very important, and at an angle of 50 degrees to PQ, as shown in figure 8.2. So if I look from above, now I'm not looking from side on as I am in diagram 8.1. In 8.2, I'm looking from above, and what I see is that the field lines are horizontal. So if I were to draw them in the diagram above, they would lie on the table. And if the field lines are lying on the table, then the frame is vertical, meaning side PQ is flat on the table. And so the field lines are 50 degrees to PQ, meaning they're not perpendicular. And so the magnetic field has components. We can call the component that is perpendicular to PQ by, and then any component that is parallel to PQ, we can call it bx. So just running on the y and x axis on the table as I look from above. We're then told that side PQ of the frame first enters the magnetic field. That's the only side inside the magnetic field, and the reading on the Newton meter changes by 1 millinewton, the small m for milli. And they say, well, use this information to determine the flux density B in milliteslas. So I don't know if it's an increase or decrease, but it doesn't really matter for now. I just want to know what the flux density is. So I can consider PQ to be just a wire going into a field. It's just a straight wire. And I have an equation for a straight wire entering a field. F is equal to B sine theta, or B is equal to F over L sine theta. F, the force on the wire, divided by the current multiplied by the length of the wire in the field times the sine of the angle between the current and the field lines. So F over I L sine theta. And all of these values are known. So I can write the force as 1, I'll write it in SI units, 1 times 10 to the minus 3 newtons, or 1 millinewton. I could just leave it as 1, because then my answer naturally would become milliteslas in the end. But we'll do that later on. The current, I was told, is 5 amperes. The length of the wire, which is the length of side PQ, is 6 centimeters. So I'm told specifically that PQ is 6 centimeters. So 6 centimeters of the wire is in the magnetic field. And that's 6 times 10 to the minus 2. I know I can say 0.06, but I've forgotten. I've simply forgotten how many decimal points a centimeter is. Write it as you remember it, then 6 times 10 to the minus 2. Be safe rather than writing the wrong number of decimal places because of a simple conversion error that's happening in your head. Multiplied by the sine of 50 degrees. So we would like the field lines to be perpendicular for the maximum force, but they're not. And so the only contribution to the force on PQ is the y contribution, by. And so by, you can see that alternate angles here should be equal, and so by should be b sine 50 degrees. So that's sine of 50 degrees. And if I calculate this, I get a flux density of 4.35 times 10 to the minus 3 teslas, which I can see is 4.35 milliteslas. And the answer asks me specifically for milliteslas. But I have to be careful. I have the force given to two significant figures. I also have the current and the length of the wire as two significant figures. So there's no reason why my answer should have 3. And so this is 4.4 milliteslas. And that's the strength of the flux density. That's the magnitude of the field at any point. Since it's uniform, at any point the field has the same strength. Now the next part of the question is conceptual. Remember, from the topic of magnetic fields onwards, A-level physics does become very conceptual. So you have to be able to state and describe and explain and suggest and predict and all of these fancy types of questions. So this question says, state with a reason whether the change in the reading on the Newton meter is an increase or decrease. We were told it is 1 millitesla, or 1 millinewton rather, but we weren't told if it's increasing or decreasing. Meaning, is the Newton meter being pulled down or is it being pushed up? Meaning, is PQ feeling a force upward or feeling a force downward? If it's feeling a force downward, the reading on the Newton meter would increase. If it's feeling a force upward, the reading on the Newton meter will decrease. Remember, the greater the weight you put on the Newton meter, the more it gets pulled downward, increasing and showing a larger value. That's why heavier weights will pull it further, and that's how you can use a Newton meter to measure your luggage, the weight of your luggage, for example. So I'm going to use Fleming's left-hand rule, and since I've already got a picture of it here, I'm going to bring it alongside, and I've made a mistake here with Fleming's left-hand rule. This was the thumb was supposed to give me the direction of the force, not the current. So, which is a test. I was just testing you. So the thumb is giving me the direction of the force. The field is my index finger, and my middle finger is the direction of the current. Now, state with the reason whether the change is an increase or decrease. Now, as I can see from the diagram, that the current flows from P to Q. So my middle finger is going to point from left to right. And the field lines are pointing into the page. So as I look at it, the field lines that are at least causing the force upward, which is By, that component of the field lines is pointing into the page. And so what it means is that the force, F, points upward. So what I will say is how I would word this is I would specifically say that I'm using Fleming's left-hand rule. Remember, there isn't any other method that we have to determine direction, since we aren't using vectors in A-level physics. So we have to use the left-hand rule to determine direction of the magnetic force. So using Fleming's left-hand rule, the force on the wire is upward. Okay, the force on the wire is upward, great, but I haven't answered the question. They asked me if the reading on the Newton meter would increase or decrease. Since the wire is being pushed upward, the Newton meter reading decreases. So it's as if I'm decreasing the force on the Newton wire. Well, actually, I'm decreasing the force on the Newton meter because the force on the wire is upward. So the force opposes the weight of the wire pulling the Newton meter downward, and so the reading decreases. So I don't have to write a long explanation, I don't have to draw Fleming's left-hand rule, but you're going to use it to determine if the force on the wire is upward. So like I say, my middle finger points left to right, my index finger points into the page, and that leaves my thumb naturally, the force pointing upward. So that portion of the wire PQ is being pushed upward, and hence the Newton meter reading decreases. The next question says the frame is lowered further so that the vertical sides start to enter the magnetic field. We are asked to suggest what effect this will have on the frame, only for 1 mark, but quite a lot of work has to go into this 1 mark. If the vertical sides now lowered into the horizontal field lines, I have something happening. I have that the y components and the x components are both perpendicular to the horizontal sides, to the vertical sides rather. So I have two components, both components of the field, that will cause a force on either of these sides. Now the horizontal or the vertical components, I'm saying vertical, but I'm talking about the By components, the one pointing straight onto the y-axis of our table, That's going to cause a force, if I use Fleming's left-hand rule, that's going to push one side of the wire in one direction and push the other side of the wire in the opposite direction, since the current is changing direction. The current is down on the left-hand side and up on the other side. So those two forces will cancel, and there'll be no net effect on the frame. But the x component, the horizontal component, will have an effect. So again, using Fleming's left-hand rule, what I have now is that the current points downward, so my middle finger points downward. My magnetic flux density now points from left to right. So what this means, if I look at the left-hand, side, the left-hand vertical face, what I have is that my force is actually out of the page, rather. My middle finger is pointing downward as the current flows down on the left-hand side, and my field lines are pointing in that direction. My horizontal component of the field lines are pointing in that direction, and then what I'm left with naturally is that my thumb points towards me, out of the page. So my thumb gives me the direction of the force, and so the force is out of the page. And so that vertical face gets pulled out of the page. But if I look at the right-hand side, it's also in the field now. Both left and right-hand faces are in the field. Then the only thing that changes is the current. The field lines stay the same. And so the force is into the page. So what this means is I will get a rotation. The left-hand side is being pulled towards me, the right-hand side is being pushed away. And so since I'm pushing with an equal force in opposite directions, I will have the wire rotating about a central axis, that is, rotating about the insulating thread, rotating about the central point. And so I will cause a rotation sort of in that way, and the frame will begin to rotate. So as soon as, we're not worried about what happens after a full rotation, etc. But as soon as the vertical sides start to enter, what effect will this have? Again, what did I do to determine this? I used the left-hand rule. You could say Fleming's left-hand rule, but again, I'm too lazy to do that, but you wouldn't be. So you can see that the Fleming's left-hand rule had to be applied here twice, and this wasn't as straightforward as a single mark would suggest, but was important that you use the left-hand rule again to determine what's going to happen. So the vertical sides will experience forces in opposite directions. If you think back to AS physics, you know that forces equal in magnitude opposite in direction basically creates a rotation. And so you can say, hence, the frame will rotate. So this is the implication of using the left-hand rule and the vertical faces or vertical sides of the wire being placed into the field. So you can see only when the vertical sides get into the field will the entire frame begin to rotate. So interesting effect, and now you know how to use the left-hand rule to answer these kinds of questions. So it's very important that you not only know the left-hand rule, but how to apply the left-hand rule. So in total, this wasn't a very long question, but it did require some thinking. Now the next question, again, it's not very clear here. This is question as numbered here. It's question 253. And this is, again, 9702. This is summer 20. So we're looking at May, June, question paper 4-1. And this is question number 8. So you can find this paper. If you don't have the Papa Cambridge questions, you can find this paper and look for this question specifically. And now I have the same question as I did before, but it's now worth 3 marks rather than 2 marks. And the definition should remain the same. The extra mark will be for saying the unit of magnetic flux density is the Tesla. And that's where the extra mark usually comes from. But you should be saying that anyway. It is the unit of measurement of magnetic flux density. It is a Newton per ampere per meter for a current carrying wire placed perpendicular to a uniform magnetic field. So when asked to define the Tesla and you're struggling to remember what it is, write down the equation for a wire placed perpendicular in a field, rearrange it for B, and build your definition from what you can see in the equation. So question B says, a magnet produces a uniform magnetic field of flux density B in the space between its poles. A rigid copper wire carrying a current is balanced on a pivot, and part PQLM of the wire is between the poles of the magnet. So only PQLM can actually feel a force due to the magnetic field if a current passes through this weirdly shaped magnet. Or through the wire rather. And this whole wire is being balanced on a pivot. So expect there to be some rotation happening, or possible rotation happening. And so this is one of the more tricky kind of questions. Now the wire is balanced horizontally by means of a small weight W. On the right-hand side, you can see a weight that is balancing. It's evening out the force on either side of the pivot so that the wire is not rotating. And we are told that the section of the wire between the poles of the magnet is shown. And we want to explain why. Now we have the North Pole on the left-hand side, the South Pole on the right-hand side. And we want to first explain why section QL of the wire gives rise to a moment about the pivot. Wow. So we have to think first what a moment means. And a moment happens when a force acts on either side of a pivot point. So basically a net force acts around a pivot point, and there is no force acting through the pivot point. So it can act at any position that's not the pivot point, and it will give rise to a moment. So that's going back to the definition of moment. So how do we know that section QL is going to give rise to a moment? Well, the first thing we can see is that QL of the wire, when placed between the poles of the magnet, is perpendicular to the field. Why? Because the field lines are pointing from north to south. So as we look at it from the side view, it's left to right. Okay. Do we have the direction of current? We do have the direction of the current. So the direction of the current is from Q to L. It's going down from P to Q, Q to L, L to M, and then out on the other side. So here the current is going from Q to L. And so again, guess which law we're going to use, or which rule we're going to use, Fleming's left-hand rule, to determine that since there is a magnetic field and a current that are both perpendicular to each other, so too will there be a force that's perpendicular to both of them. Now, the force, if I use Fleming's left-hand rule, is going to be a vertical force, specifically downward. Doesn't really matter if it's downward because a moment would happen either way. So how would we go about explaining why there'd be a moment? Now, they didn't say it needs to be clockwise or anti-clockwise. They just simply said it needs to be a moment. Now, the first thing we need to state is that the wire is perpendicular to the field. Or you can say the current is perpendicular to the magnetic field. Remember, that's very important for us. So the wire being perpendicular to the magnetic field means the current is perpendicular to the magnetic field. And the current in the wire is hence going to feel a force. So the current in the wire experiences a force. But the force is important here because we are asked to define if a moment is going to happen or not. So we'll specifically say not just a force, but a vertical force. Because a vertical force is going to cause a moment, because look at the pivot. The pivot is placed in such a way that only a vertical force is going to cause a moment about that pivot. And if you want to, you can say downward as a way of remembering. And the direction I get downward is from using Fleming's left-hand rule. So there's a vertical force which is downward. And importantly, for the third mark, you have to say it doesn't act through the pivot. It doesn't act through the pivot point. Because you will not have a moment. You could have a force, a net force acting through the pivot point, but that doesn't cause a moment. That would just cause the whole wire to move up or down. And so Since the wire is perpendicular to the field, there's going to be a force that is perpendicular to both of them. Current is into the page, the field is from left to right, and so if my middle finger points into the page, my index finger points to the right, my thumb will point downward. And it's going to be difficult with this diagram, but my thumb is going to point, or my index finger is going to point from left to right. My current's going to point into the page, and so I'm going to have to flip the thumb here, but the thumb would be pointing downward. And so the force would be downwards. The force on section QL would be downward, causing a moment and causing the wire to move around the pivot point. Next, we are asked to explain why sections PQ and LM of the wire do not affect the equilibrium of the wire. So PQ and LM are now lowered into the magnetic field. Even if they were always in the magnetic field, they aren't actually causing anything to change with regards to the equilibrium of the wire. But again, if we think about this, I have a current downwards in PQ and upwards in LM. And so if I have a current down, my middle finger is downward, and my index finger from left to right, but from LM, my current now flips direction. My middle finger points upward, but my index finger remains the same. So on PQ, I have a force that is pulling out of the page. And on LM, I have a force that's pushing into the page. But since the magnitude of the current and the magnitude of the field remain the same, so too does the magnitude of the force. So I have a force pulling and pushing with the same magnitude. The two cancel out and they don't affect the overall equilibrium. If I push and pull a box with the same force on either side, nothing happens. The box doesn't move. There's no net force. So what I can say is that the forces are both horizontal. So as we look at them, they are horizontal from our point of view. Or you can say they're along the same line. Specifically, both of them are horizontal. And they're equal in magnitude. And that's very important. If they weren't equal in magnitude, then there would be a net force, and that would cause the wire to be pushed in to the page or pulled out of the page. So specifically, I'm going to say equal in magnitude for both faces, but in opposite directions. We have horizontal forces acting in the same line. They're equal in magnitude, but opposite in direction. And so they cancel out. We have two forces that are equal and opposite, and we know what that means. If they act on the same object, there's no net force on the object. So you can see it's very important to understand that when a U-shaped piece of wire goes between a magnetic field, you should be able to apply the left-hand rule and move your fingers around so that you can identify why there may be rotations or pivots or moments, etc. And so these are useful applications of the left-hand rule. Now that's not the end of the question. The next part of the question tells us, well, here's the actual length of section QL. The length of QL is 0.85 centimeters. The perpendicular distance of QL from the pivot is 5.6 centimeters. And they give us a whole lot of information. When the current in the wire is changed by 1.2 amperes, W is moved a distance of 2.6 centimeters along the wire in order to restore equilibrium. The mass of W is 1.3 times 10 to the minus 4 kg. Show that the change in the moment of W about the pivot is 3.3 times 10 to the minus 5 Newton meters. Now it's very easy to get overwhelmed because I'm given 1, 2, 3, 4, 5, 6 pieces of information, and I'm asked to show what the change in the moment is. I'm given 5 pieces of information and then said, show that this is the moment. This should not overwhelm you because it should do the opposite, actually. It should encourage you because you are given quite a lot of information, which means that whatever I need should simply be put into some equation. Now QL, our length of QL is given to be 0.85 centimeters, and the perpendicular distance of QL from the pivot point, that is the distance there, which is already marked, is 5.6 centimeters. So they marked it in the diagram. It's easy to understand what this diagram looks like. The current is then changed by 1.2 amperes, which means the equilibrium is disturbed because the wire begins to experiences a moment, and we have to move the mass W in order to restore equilibrium. We're told what the mass of that weight is. So how do we find the change in moment? So what do we know? We know that the moment changes when the current changes because the force changes. So the change in moment, if you remember, is the change in force times the change in distance. But I don't need any complicated forces because what I simply need is the mass of the weight that is moving, mg, times the distance it moves. I'm not asked to calculate the moment, I'm asked to calculate the change in the moment. And so the change in the moment is the weight of the mass, which is the object moving, multiplied by the distance that it moves. And so I can just use the values as given, 1.3 times 10 to the minus 4 kgs times 9.81, which is g. I can go to my data sheet if I'm confused about that, times 2.6 centimeters, which is 0.026 meters. Again, you can write this as 2.6 times 10 to the minus 2 if you are uncertain of the decimal points. What you get is that the moment changes by 3.3 times 10 to the minus 5 Newton meters. So I had equilibrium, I increased the current, which caused the entire wire to move around its pivot. It's very difficult for me to calculate what the moment would be, the change in moment would be from those forces, but I didn't need that because to balance out the moment, I would just have to figure out what the change in moment is on the other side, that is how far I've moved the mass to restore equilibrium. And so mg delta x would be a much cleaner way of calculating the change in that moment. So I get 3.3 times 10 to the minus 5, don't forget the units is Newton meters, which is what they asked us to show. The last part of the question says use the information in 1 to determine the magnetic flux density between the poles of the magnet. Now this is where it gets a little bit more complicated. What I know is that the force that's being applied to the wire must equal the force that's experienced on the other side when we move the weight in order to balance the wire. So this force, I know, is B times the change in current times the length of the wire in the field. So if I want to know the change in force on one side, it must be equal to the change in force on the other side. But the change in force is simply the change in moment over the change in x. And so I can write this as the change in moment, which I've calculated, divided by the distance over which the weight has been moved, which I was told is 5.6 centimeters. But what I actually want here is B. I want the magnetic flux density. So I can write this as the change in moment divided by the length of the wire in the field, or the length of the section QL in this case, times the change in the current times x. Remember, changing the current is what causes change in force on that section of the wire. So this change in moment is 3.3 times 10 to the minus 5 Newton meters divided by the length of section QL, which is 0.85 centimeters, or 0.85 times 10 to the minus 2, multiplied by the change in current 1.2 amperes. Remember, we weren't given absolute currents, but just changes in currents, multiplied by 5.6 times 10 to the minus 2, the distance through which the mass was moved. And so this actually gives me the magnetic flux density. And what I find is that this is 0.058 teslas, or 58 milliteslas. But again, this is specifically asking me to calculate this value in teslas. So you can see that some knowledge of AS physics, quite significant knowledge of AS physics, is required, even though this is a question purely on magnetic fields. And we had to manipulate our knowledge of moments to be able to find the flux density. You could use some dimensional analysis to figure out how to calculate this, but this would always ensure that you get a final answer that's in Tesla, meaning you're calculating the flux density. And remember, flux density for anything in the lab will generally be on the order of milliteslas or microteslas even. But very rarely will you have magnetic fields where the strength of the field is 1 Tesla or 10 Tesla. That's very energetic objects like MRIs and so on. And so that was a 13-mark question. There was a lot to that question. Mathematical calculations that were quite tricky, conceptual questions that required a bit of thinking. And these are the good types of questions that will help you bolster your understanding in a otherwise very difficult topic. Magnetic fields is not an easy topic and will not be. The next question, which I'm going to do, which will be the last one for this video, is again quite similar. These magnetic field questions, as you can see, are quite similar. I will do another video on electromagnetic induction that has its own paper with its own questions, but although it is part of the same chapter in A-level physics. But the next question is very similar: magnets and wires and currents. This is 255 or summer 2018 question paper 4, variant 1, and this is question number 9. So we are told that a rigid copper wire is held horizontally between the pole pieces of 2 magnets, as shown in the figure. The width of each pole piece is 8.5 centimeters. The uniform magnetic flux density in the region between the poles is 3.7 milliteslas and 0 outside this region. The angle between the wire and the direction of the magnetic field is theta, and the current in the wire is in the direction shown in figure 9.1. So we have current from left to right. And we don't know the angle theta, so that's going to come back at some point. Now, by reference to the side view, very specifically they said by reference to the side view in bold, state and explain the direction of the force on the magnets. If you do have time in an exam, it might be a good idea to underline keywords so that you make sure you're answering the question correctly, or at least answering the correct question. So I'm going to look at the side view and use that as my reference point for directions, and guess what? I'm going to use Fleming's left-hand rule again. The direction of current is left to right, so my middle finger points from left to right. The magnetic field points into the page, north to south points into the page. So my index finger points into the page. This is quite easy, as all that leaves is that my thumb points upward. So middle finger left to right, index finger into the page, and thumb upward. Let's see if I can find Mr. Fleming's left hand. We found Mr. Fleming's left hand, but the picture is identical. So we have current in this case, which is left to right. Again, very difficult to rotate this. I can't rotate the picture. I'm just rotating that. So current left to right, field into the page, and so that leaves my thumb pointing upward. And so what I have now is my force on my wire pointing upward. Great. I've got 2 marks, have I? Well, no, actually I haven't. I've got 1 mark. Because the question specifically says, no, I don't want the force on the wire. Remember, Fleming's left-hand rule gives us the force on the current, which is in the wire, but the question says I want the force on the magnets. So I'm going to say, using Fleming's left-hand rule, the force on the wire is upwards. Great, I can rest easy. But no, the question asks me what's the force on the magnets. Now, if the magnets are exerting a force on the wire that's upward, then our other friend, Newton, has a law that says, well, the wire must exert a force on the magnet that must be equal in magnitude, and opposite in direction. That's Newton's third law. We can call it a reaction force. It is a reaction force. The reaction force on the magnets is downwards. So be very careful to answer, make sure you are answering the question that is asked. The left-hand rule is great, but it only gives you the force on the wire. The question asks what's the force on the magnets. So by the third law, which you must write down, the reaction force on the magnet is downwards. So yes, the force on the wire is upward, but that only scores you 1 mark. You have to answer the question. The force on the magnets is then downwards. Question B says the constant current in the wire is 5.1 amperes. For angle theta equal to 90 degrees, calculate the force on the wire. And this is your time to shine. F is equal to Bill. Specifically, I'm going to say F is equal to Bill sine theta, the force on the current carrying wire. This is bread and butter for most of you. What's the magnetic flux density B? It's given as 3.7 milliteslas. 3.7 times 10 to the minus 3 teslas. The current was given as 5.1 amperes, as we see here, two significant figures. And the length of the wire, they told us, is 8.5 centimeters. And that is completely perpendicular to the field. So the 8.5 is the length of the wire inside the field. 8.5 times 10 to the minus 2 meters times the sine of 90 degrees. Hooray, sine of 90 is 1. This leaves us with 1.6 times 10 to the minus 3 newtons. I need this to two significant figures, so this is 1.6, not 1.60, times 10 to the minus 3 newtons. And so that's the force on the wire if the wire is perpendicular. The angle theta is 90 degrees. Now the next part might be a bit confusing. It's a 1 mark question, but it's a calculation question. The angle theta is changed to 60 degrees, and the length of the wire in the magnetic field L is now 8.5 over sine 60 centimeters. Calculate the force on the wire. Well, this is strange. I already know the equation for the force. Why are they asking me this again? F is B times I. The length now, L, is 8.5 over sine 60 degrees times the sine of theta, sine of, oh, I see, times the sine of 60 degrees. And so this simply becomes BIL, just like it was before. I don't need to do this calculation because I've already done it. I've done it in the previous part, and I got 1.6 times 10 to the minus 3 newtons. What does this mean? This means that the force is the same if I change the angle of the wire. It turns out, irrespective of what the angle of the wire is, if I increase the angle, but at least keep the entire portion of the wire inside the field, a greater length of the wire will be in the field. If it's perpendicular to the field, then just that length of the wire will be in the field. But if I change the angle, more of the wire is in the field. So even though it feels a lower force per unit length, there's a greater length. So the overall force of the wire will be the same. So I can take this wire and I can fluctuate the angle theta as I want to, provided I keep the entire section within the field. The overall wire, the total wire, will still feel the same force. I bet you didn't know that. And that's the thing with Cambridge. You'll always find questions that will make you discover new things and even question whether you actually knew what you were talking about. But yes, the force is the same, and hence there's only 1 mark for this calculation. So be very careful about a question that's novel like that. It's possible for something to maybe throw you off slightly. Next question says the constant current in the wire is now changed to an alternating current with a frequency of 20 Hertz and a root mean square value of 5.1 amperes. It's at this point that most of you probably checked out and left the paper and ran away. Now the angle between the wire and the direction of the magnetic field is 90 degrees, and they ask us on the figure below to sketch a graph to show the variation with time of the force F on the wire for 2 cycles of the alternating current. So we were living a very happy life doing magnetic fields, and now they ask us to include alternating currents. How am I going to know how a force varies with time? Well, I don't really need to know how the force varies with time, at least for now. But what I do know is the current is varying with time. But what I also know is that the force is related to the current. If all I do is change the current, but I leave the length the same, I leave the flux density the same, then the force is proportional to the current. As the current fluctuates, so too does the force on the wire. So I can say F is proportional to I, meaning if there were such a thing as RMS force, then it would be proportional to the RMS current. And the maximum force, well, there is such a thing as RMS force, there's RMS any quantity. But the maximum force would also be proportional to the maximum current. When I have the maximum current, I have the greatest force. When I have the weakest current, I'll have the lowest force. And so the maximum force is equal to the square root of 2 times the RMS force, times the value of the force that you'd get when the current is its RMS value. But that I already know, because the RMS value is 5.1 amperes. And it's the same 5.1 amperes that I used in the previous question. And I know that force. That RMS, quote-unquote, force is 1.6 times 10 to the minus 3. So that's the square root of 2 times 1.6 times 10 to the minus 3. So this is my maximum force. Again, you don't have to do this calculation in such detail. You could do it aside. But I get 2.3 times 10 to the minus 3 newtons. Aha! So now I can identify the peak points of my graph. And I'm going to use just an arbitrary scale. I'm going to use 4 blocks for my peak, and I'm going to say that's 2.3 times 10 to the minus 3. The newtons is already included in the units. And obviously on the other side, I'm going to use 1, 2, 3, 4 blocks as well. And I'm going to say minus 2.3 times 10 to the minus 3. The current is changing direction, and so too will the force. The force will change direction as well on the wire. It'll push in one direction and then push in the other. However, I know that a current is varying sinusoidally. So force is going to vary sinusoidally. But I don't know the period and the frequency of the sinusoidal variation. Well, actually, I do know the frequency, but I don't know the period. Luckily for me, I know there's a relationship between period and frequency. T is 1 over F. Period is 1 over frequency. 1 over 20, it will not surprise you to know this is 0.05 seconds. Which means that one complete oscillation of the force, of the current, and hence the force, will happen in 0.05 seconds. So I'm going to mark off all the important points in the diagram, and then I'm going to sketch a graph. But the graph says specifically, sketch the variation with time of the force for only the first 2 cycles. Be very careful to read the question properly. And so I'm only asked to sketch, but I should sketch it sine rather than more straight or logarithmic or parabolic or whatever. It should look like a sine curve because that's what it is. And so this is going to be very difficult for me to draw, but you imagine that you're very good mathematicians and you know how to draw a very good sine graph. I promise if I had a pencil, this would be a much easier task. But as you can see, it's a curve. It's not a spiky up and down. Curves, it has a maximum and minimum, and you can imagine it looks very neat. Promise if I was doing this with a pencil, it would look a lot better, but you can see where I'm going for here. So this is indeed a sine curve, but I'm also very specific to make sure that I'm only including 2 cycles. And so that's the first 0.05 seconds, which is my period. I'll write it here so it's easier to see. And actually, I don't need the seconds because time is already, the unit's already given. And then the second cycle, after 2 cycles, the time will obviously be 0.1 seconds. And so I've now sketched the graph of the variation with the force with the time. And as you can see, I needed to plot the special points and then sketch the graph from there. But remember, I don't know what the force or how the force would vary if the current is alternating. But I do know that the current varies sinusoidally, and the force is proportional to the current. So the force will also vary sinusoidally. And so the force has a maximum, it has a minimum, it has an RMS value, and at some point the force will be zero when the current is zero and changing direction. For a brief moment in time, there won't be any force on the wire. So again, you don't need to do all the side working that I did, but you would need to find the peaks, because when you sketch a graph, you have to have the important features. The important features of this graph would be the max, positive maximum and negative maximum, and also the period of the graph. So you'd have to have some sort of a side working. And yes, that's 3 marks, so it's a significant amount of marks, but also a significant amount of time that you would require. So you can see, although you were never explicitly taught about the relationship between a force and an alternating current for a wire in a magnetic field, you could be asked a question. And you have to put together pieces of information from multiple topics to understand how to answer this. So I'm only doing these 3 questions for now. We will come back to this paper at some other point, but in the meantime, as you're preparing for your final exams, be sure to complete as many of these as you can. Do your studying on the concepts, but also these questions are very helpful. They are set by the same people who are setting your exam, so it might give you an insight into what type of questions to expect. But practice will make perfect. And so continue with these, continue with the other topics rather. There are many, but they will also be very helpful, and they should pay off in the future, in the long run. So until next time, until we do another video solving problems on a different topic, please like, subscribe, comment. Let me know if these videos are helpful in the comment section, and I'll see you again next time on Everything is Relative.